Continuing with the composition that generates VR renderings from 3D scenes, in this video, I want to present a possible workflow, in which the feature is used to integrate 3D elements into an image, shot in 360 degrees. It is a hypothetical composition, much less complex when compared to a professional production. The intention here is to present fundamental approaches, and a way to carry them out for the VR format. As is normally done in any other composition of visual effects with CGI insertion, where the elements are separated into partitions and rendered in passes, in this example, the same happens. We will see how the elements were separated by distance from the camera, or were separated to simulate reflections, on the facades of buildings and on the water surface. We will also see how it is possible to make 2D and 3D interventions in the photographed architectural elements. This composition is available for download, at the link indicated in the video description. The composition is organized in a conventional way. On the left, we distribute the 3D elements, separating them into partitions, necessary to render the three-dimensional scene in several different passes. In the center, 3D to VR rendering flows are distributed. They render the scene partitions as passes, in the equirectangular output format. It is necessary to use a rendering flow for each partition of the whole 3D scene. Here in the right part of the composition, the actual post-production happens. The generated passes are treated with color grading, adding effects, such as blur, soft glow, displace and cutouts through masks. Let's look at the 3D scene with its models and partitions. Here in this first flow, we see the modeling of the flying saucer, using 3D shapes native in Fusion. At this point, the light cone is not yet added. In this Merge 3D, the light cone is added to the flying saucer. Here we have a 3D model of a car, downloaded for free from the website turbosquid.com. It is duplicated and added to the flying saucer with the cone, forming a set. This boat was also downloaded from the same website. Here we create two copies, using two transform 3D nodes. And here, in this Merge 3D node, we add the copies to the flying saucer with the cone, forming another set. So we are left with three versions of the flying saucer, a solo version, another with cars, and a third version with boats. The boat model, disconnected from the flying saucer, also takes part in the scene, anchored in the river and close to the camera. The flying saucer solo version is duplicated and transformed, forming the first partition. It is connected to the input 3D node of the first rendering flow to generate this equirectangular image. Here, we have the VR image, shot on location, on the outskirts of Canary Wharf, in London. The image was downloaded for free at hdrihaven.com. So, here we have the first post-production moment, where the image goes through color grading, as well as the rendering pass of the flying saucer, which also receives other effects and masks, integrating into the photography landscape as if the flying saucers were amidst clouds. These two versions of the flying saucer, one with cars and the other with boats, are distributed in two small sets. In this set, copies of the models, created with Transform 3D nodes, are positioned farther from the camera and farther from mirrored glass, and therefore do not produce reflections. In this other set, we created the copies closest to the camera, within the scope of the mirrored glass and the river's water surface. Therefore, they are copies that reflect your images. These two sets come together in this Merge 3D node to form the partition we call the main scene. So, the main scene connects to its respective rendering flow, and thus one more pass is rendered. With post-production tools, we have achieved this result. It enters the final composition flow as a layer above the reflection layer. It is also necessary to generate a rendering pass that acts as a mask, which restricts certain effects to light cones only. Returning to the 3D scene. Here are aligned a series of tools that we activate only to render this specific pass. There are several overrides that assign matte properties, or visibility properties, and also replace material tools, to assign a 100% white material to the light cones. I'll disable the nodes. Here, as I said before, the partition with the main scene is separated into two sets. The one that contains the non-reflecting copies of the models, and the one that contains those that effectively generate reflections. In this set, we arrange 6 Transform 3D nodes that operate to generate each reflection on each mirrored surface. It is necessary to assign an expression in certain parameters, so that the Transform 3D node creates a symmetrical copy of the model, by using the mirrored surface as its symmetry plane. For example, if we look at the boat, we can see more clearly how this effect occurs. The actual boat, and its symmetrical copy. The Transform 3D nodes are connected to this 3D merge, to form the reflection partition. Then, it connects to the corresponding rendering flow, and thus, we have the reflection pass. Again, it is necessary to generate a specific pass to mask the light cones, by activating the tools shown before. With post-production, we get this result. We will see later on the 3D model for the water surface, which generates this pass. The image controls the displace effect, which causes this appearance of flickering reflexes in the waves. This pass needs to be generated to mask the reflections layer, so that it is restricted to the building's mirrored glass. And so, we get this result in the final line of the composition. At this point, the reflection layer is the second on the final line. Following the line, we put the main scene layer over it. Let's look at the next partition with the water surface. Here we set up a fast noise, which controls the display's 3D node, to create water ripples. This replace material node represents one more scene partition. Here, the fast noise operates as texture. The water surface model is rendered by its respective rendering flow, and thus we have the pass that acts in the 2D displays, in the post-production stage. The water surface is also used to cut the hull of the boat, in its isolated version, separated from the flying saucer and which is part of the main scene. For this, we use an override tool that assigns the matte property to the surface. Let's disable override for a moment. So we can see the water surface in contact with the boat's hull. But when we activate the override again, it proceeds with the clipping. The remaining two partitions are part of a model where plain 3D shapes represent architectural elements from the shot location. This partition generates the mask that controls the reflection layer cutout. It gathers objects that represent the facades of the buildings, and who get textures edited from images captured from the VR itself, as we will see later. The partition feeds a 3D input into our rendering flow, and, at the output, we have this image in equirectangular. The partition with interventions in the pedestrian square, next to the camera, also comes from the reference model. Other geometries are added to the scene, modifying the original appearance. The textures are also edited from images captured from the VR shot. In order to create this reference model in a manner consistent with the actual photograph space, two approaches are necessary. The first of these is the use of the VR shot image as background. Here in this wireless link node we connect our original VR with color grading applied. We need to use this background image to position the planes. Let's see the following. If we apply a VR image as texture of a sphere, and if we place a camera in the center of the sphere, this camera will view the image in the correct perspective, without the curvature distortions of the equirectangular shape. Exactly the same way by 360 view option on Fusion. They are identical views. If we do the modeling on a 3D merge that also contains the sphere, then we can align the three-dimensional meshes according to the photographic reference. Let's assign transparency to 3D shapes, to see better how they align with architectural elements. Let's choose the perspective view, outside the point of view of the central camera. So this is one of the modeling approaches, that is, the VR image itself used as background. The other approach is to study, as much as possible, the dimensions, the scales, the proportions of the shot place, either through access to architectural and urban designs, maps, or by visiting the place and collecting all possible spatial dimensions. So let's see the following. By searching Google Maps, we discover that the shot was taken at this location, Canary Wharf, in London. Here, the place where the camera was positioned, and its surroundings. Here, the stairs, the wall. Here, the building with the curved facade. This is this building. These are these stairs. Google Maps provides us with a scale reference for the image and, with it, we can do this type of investigation, which is approximate, is not exact, but fulfills the needs of the composition. Here we take the scale and set up a ruler. We can deduce what are the real distances of the mirrored facades in relation to the position of the camera. We can consider the camera as X and Z axis origin, and use the same orientation in 3D modeling. See mirror 1, for example, placed 50 meters from the camera, on the X-axis. This is mirror 1, and here, in position X, we put 50 meters. On the X-axis of mirror 2, we place 100 meters. This is what was deduced on the map. Mirror 3 is 30 meters away and mirror 4 is 35 meters away from the camera. Returning to fusion, mirror 3 placed at 30 meters in X, and mirror 4, at 35 meters. It is important to find and use these dimensions closer to reality, because it is not always possible to align the planes based only on the perspective of the photo. It is always more difficult to deduce at what depth the elements are positioned. Let's look at the following situation. Here we have our 3D flow for VR. But here it is operating in a reverse way. Let's see. This is a 3D scene. I will remove the background sphere. A 3D scene like any other. If we want to use the flow in the conventional, direct way, we place the scene in the input 3D node. The 6-camera rig shoots the scene in 360 degrees, and generates 6 renderings. Each rendering, from camera 1, camera 2, camera 3, etc., will feed a corresponding projector rig. The projectors project the images onto the surface of a sphere, here in this projection room node. A sphere receives the catcher tool. Let's activate it. So here we have the sphere receiving the projections. As a result, we get an equirectangular image of the 3D scene. This is the direct use of the flow. But now let's interchange the geometries from each other's place, and thus use the flow in a reverse way. This is the flow's potential that sets it apart from other VR compositing features. Let's insert the sphere into the input 3D node. And let's insert the 3D scene into the projection room node. For the 3D scene, let's activate the catcher tool. As a result, the surfaces of the 3D scene receive projections from VR photography. It is important to note that the sphere and camera rig must share the same position. It can be the 0 point, at the origin, or any other coordinate, as long as it is the same for both. This must be done, so that distortions do not occur. Let's connect the previous cam to the input 3D node. It is a point of view from which the sphere is visualized in a natural way. It is the same point of view of the camera rig. Let's see the rig renderings. Camera 1, Camera 2, Camera 3, Camera 4. These images feed the projectors, and are projected on surfaces connected to projection room node. Thereafter, if we connect each geometry from the scene, one by one, to the projection room, for example, mirror 1. We choose the OpenGLUV renderer mode and choose convenient dimensions for the image frame. We can get this image extracted from the VR, without the spherical curvature and without the perspective distortions. They are frontal images, with straight lines, easy to manipulate, ready to be used again as textures of 3D objects. Let's connect the mirror 2 object, only him. Again, the OpenGLUV renderer mode. With the image width and height framing a desirable proportion, similar to the plane proportion. And so on. We save the renderings to disk. Opening the images in an editor like Photoshop, we design the mirrored glass masks. Notice how curvature and perspective distortions have been eliminated, and how the images have straight, horizontal, and vertical lines, which makes editing much easier. The edited images return as textures to the same objects. Mirror 1, Mirror 2, Mirror 3, and with that, we have a 3D scene partition, aimed to generating the mask for the reflection layer. Likewise, these other images, extracted from VR, are edited on this partition. They also return as textures to the same objects. It is necessary to create a link between the planes that represent the facades of the buildings, and the partition that generates the reflection pass, in order to position the models in a realistic way. And to show this, we created here an area that gathers the partitions around a single merge 3D node. So that we can make comparisons between them. This approach is possible if we install a feature in Fusion through Reactor. By opening the reactor and enabling the wireless 3D fuse, we get a tool similar to the wireless link, but created to connect 3D content. So let's connect the reference model with the mirrors, and add the reflection partition. Let's bring the main scene partition to merge 3D node. Now we will see the link. If we move the mirror, the model placed in the reflection position will move symmetrically in relation to its original source. Not only in position, but also in appearance, symmetry occurs. We get this effect if we make a model go through a transform 3D node, with an applied expression. This expression uses the position parameter of the object that acts as mirror. In this case, the mirroring occurs along the x-axis. The parameter must be multiplied by 2, and here, at the scale, on the same axis, we change the value to -1. In addition, if we move the source model, its reflections move symmetrically. This also happens with water surface. Let's add the partition with the model. There is also a link between the boat and the water surface. The boat goes through a transform 3D node, and here, the symmetry axis courses to y. The y parameter of the water plane position is multiplied by 2, in the expression. And here, again, we change y-axis scale value to -1. If we change the water level, the reflection of the boat moves symmetrically. Or, if we move the boat, the same effect occurs. We no longer need the reflections and main scene partitions. This plane, when catching a particular section of the VR image, becomes a reference. Let's see. Let's activate the catcher tool again, here in reference model scene. And here, in the caught image, we can see the luminous sign in red, at the top edge of the plane. At the bottom edge, we see its reflection. Again, the luminous sign and its reflection, symmetrically below the water surface. Therefore, we find the right water surface position, halfway between the sign and its reflection. Let's go back to reference model. We saw earlier that these planes, mimicking the building's facades, were positioned with the help of information gathering. We went to Google Maps, and discovered the real distances from the facades, in relation to the camera. Here, in this central region, closer to the camera, we need to position all these planes in a convincing way, with no clues about the element's real dimensions. Let's look at the following situation. Let's isolate the hedge. We have a plane that is receiving projections. If we move the plane closer to projectors, the hedge decreases in size. Or, if we move away, the hedge grows. So what could be the approach to defining an ideal distance? In that case, we can use a human scale reference. we can apply a texture to a plane with human dimensions, about 1.75 meters high. Place it very close to the plane that receives the hedge projection, and link these two objects. If we move the hedge, the human figure follows. Let's disconnect the floor from the scene to see better. Now, moving closer to projectors, or moving away from them, we realize what is the ideal ratio between the human figure and the hedge. In this way, we were able to pin the position of the first element, in a reasonably, convincing, and realistic way. Reconnecting the floor. It is also a plane receiving projections. We can try to find out the ideal height from the floor, by observing the ideal touch point with the hedge. Here, moving down. Let's move closer. Let's go up with the plane until we check a touch point with the hedge, that seems consistent with reality. Done. After the pinning of floor's height, let's look at these other elements. See what happens when we bring the plane closer to projectors, and when we move it away from them. We are able to find touch point and pin the object. Likewise, we are able to position the wall opposite the hedge plane. Repeating the procedure, moving closer to projectors, and moving away from projectors. Until the touch point is found. So, based on a reference we know, in this case the human figure, we can do a 3D modeling within a convincing scale, close to the real scale. Recalling that these objects are part of the reference model, that was used to catch images from VR. Then, we have the image of the hedge, the face of a block, the face of the opposite block, the wall, and the floor. All of these images are saved to disk, edited, and returned to the same objects as textures. Let's look at the partition with the pedestrian square interventions. For example, the floor object. Here, the caught image is edited. And returns to the same object as texture. The same is true with the wall object. The caught image undergoes several interventions, and returns as texture to the same object. Also here, image receiving interventions and being reapplied as texture. Here again. New objects were created, but always based on the caught image. Here, for example, we create 6 faces of a cube from the same base. Here, the cube is duplicated several times. For this other cube, same procedure. The caught images are the basis of several interventions, until they become textures on 2 sides of the cube. This entire partition splits at 2 output points. One of them gather the objects with the final textures, and additional lights to relighting the model. This output connects to a VR rendering flow and generates this pass. With the same output point, it is possible to generate the ambient occlusion pass. So, from here, we make a connection with a new rendering flow. And, between the render and the projector, we place an ambient occlusion node. Here, the final pass in equirectangular. At this other output point, we replace the whole partition material with a white, opaque material. A new group of lights is applied, but this spotlight has shadows enabled. We connect this output point to a new rendering flow. And so we get the shadow pass of the model. So, here, we have the pass with textures and new objects. The ambient occlusion is added to it, after treatment. And then the shadow pass is added to complete the scene. The scene enters the final line of composition as the last layer, so we get the final result.